loud. Perfect. Thank you everyone for being here. So on behalf of the ASAP leadership team, I wanted to welcome you to our first webinar this year since getting awarded by NSF for our Phase 1 award. So we are the Center for Advanced Semiconductor Chips with Accelerated Performance. And this is an industry university cooperative research center. I'll just briefly update you on what that is. So an IUCRC, short for Industry University Cooperative Research Center, is basically a program that NSF has been running for a number of decades now, which brings industry, national and DoD labs and universities to work together on pre-competitive research ideas that are of mutual interest, and industry would find them highly relevant and guide us based on their research needs. This program is financially supported by NSF to help us with our administrative costs, and we also collect membership fee from our industry members. For ASAP, our membership fee is about $60,000 per year. Our university also supports us, of course, by providing infrastructure to conduct the research, as well as with reduced overhead costs. We're very thankful to all the companies that I've listed here on the right-hand side that were present at our Spring 2023 meeting that was held in person on our campus on April 20th and 21st. So we have TSMC, Raytheon, Lincoln Labs, Sandia, AMD, LPS, AFRL, IBM, Synopsys, Intel, and LG. Most of these companies are also supporting us as members of ASAP in year one. If you're interested in joining our center, please reach out to me or Mallory for documents that are related to our membership. So it's often asked, what is the value proposition of an IUCRC or ASAP? I think by supporting us, you get access to faculty members. We have faculty members that are represented from many different departments within the College of Engineering, material science, electrical and computer engineering, chemistry, physics, mechanical engineering, and so on. You're also able to leverage our existing infrastructure. I'll talk a little bit more about the available resources and facilities that are on our campus for high quality synthesis, device fabrication, characterization, modeling, and simulation. You also get access to our undergraduate and graduate students. I also have a couple of slides to talk about our workforce development plans in microelectronics and semiconductors. We provide access to IP. You're also able to leverage NSF dollars because for this particular center, we will only charge you 10% overhead as opposed to 60% that is otherwise charged for sponsored research. There's a high return on investment because you are able to get access to all the projects that are supported in the center, all the IP that's being generated from the center, as well as preprint, students, faculty expertise, and so on. So you can consider ASAP as an excellent open innovation program where you're able to work together with companies and labs that have similar interests but are representing different sectors of the industry. So just a very quick timeline. Those of you that are joining us for the first time, I just wanted to tell you that this center, we started working on the center in 2021, and from 2021 to 2022, we were planning the center, getting support from industry members, really trying to understand the specific technical areas that we would like to address when we went forward with a Phase 1 proposal to NSF. We submitted our Phase 1, and luckily we were very successful. We got our funding approved in January of 2023, which officially launched our Phase 1 center. When I say Phase 1 center, this is a 5-year effort with a possibility to do another 5 years for a Phase 2. And at that time, at the end of 5 years, we will have to recompete. And when we got the center, we invited faculty to submit white papers on the research needs that industry members had provided to us. In April 2023, we met on our campus, and our industry advisory board selected projects. We presented all the projects to them, and they voted on projects that would be funded for first year of our center. So right now, today is August 24th, and so we're here today because what I wanted to do was give you an overview of our spring meeting, and I know that many of you were there. I just wanted to give you updates from that and also give you a showcase of all the funded projects for year one. present some of our workforce development initiatives in microelectronics. And then for each of the projects that we will present today, there will also be plans for the deliverables and the timelines for the remainder of the first year, which will end next year, end of July 2024. We are also planning a fall industry advisory board meeting, and the tentative dates are set as December 5th and 6th. Because of some very strict timelines, we are expecting to run this meeting as 2 half-day meetings, which will be fully virtual. The purpose of the fall meeting will be to review progress on funded projects. There will be a number of faculty and student presentations, which will be much more in-depth compared to what we will talk about today. There will also be poster sessions and a discussion of our 2024 plans moving forward. We will come back to our campus for our spring IAB meeting, which will be held in the 3rd week of April 2024. Pardon, this is an error. It should be 2024 next year. So this will definitely be in person, and this will be an important meeting because we will not only be reviewing projects from year 1, we will also be presenting some new projects to you for consideration of funding in our academic year 2024-2025. So that is our tentative timeline moving forward. I wanted to show you our core team as well as the support that we've been getting from NSF. So we have myself and Professor Cheng Zhao here, who's serving as the Associate Director. We have co-PIs on our team as well, bringing in valuable strengths in areas related to material synthesis and 3D nanoscale architectures, as well as energy efficient computing, both at the circuits and systems level. We're very fortunate to have Irfan Ahmed, who's serving as our Innovation Director, as well as Mallory Gorman, who is our Operations Manager, and she has been the one that is really spearheading this webinar and was the one to kind of reach out to you for registrations and so on. So thank you, Mallory, for helping us with this. I know that Todd is here as well. Thanks, Todd. Todd is serving as our NSF evaluator for the center. And we're thankful to Prakash, who's serving as our NSF program manager. So that is our core team. All of us are located at UIUC, other than NSF, of course. So what is our center science? What is the basic mission and vision of our center? So one of the things in today's computing, one of the biggest challenges in computing today is the data communication challenge, because you consume a lot of energy and time in order to kind of constantly fetch data between memory and processor. And this is an issue that is not just present in the digital domain, but if you're thinking about mixed signal and RF domains as well, similar issues that are related with data communication emerge. Therefore, in order to cater to this, we decided to build a center that would allow us to address this challenge in a full stack cross-layer solution by implementing these 3 themes that I'm showing in the middle of this slide over here. Our first theme, our research theme of the center, focuses on materials discovery. This is for both electrical and optical interconnects. So we have computational efforts as well as experimental efforts. And we can bring those capabilities in order to design these new interconnects and benchmark them against conventional solutions. Our theme 2 is on heterogeneous integration, which will allow us to understand how different types of devices and materials can be integrated within a silicon CMOS platform. And finally, in theme 3, we will try to understand how these new kinds of materials and devices and interconnects that we're discovering can yield circuits and architectures that are able to reduce the energy consumption and help us with some of the data communication challenges that I was talking about earlier. Our hope is that by working in these 3 themes, we will support the mission and vision of our center, as well as allow our companies to really look at the solutions that we're developing holistically and really generate that leadership in critical technologies, including high-performance computing, advanced manufacturing, 5G, and beyond. We understand that our industry members are representing different sectors. To be able to cater to them, all our projects that we are bringing to you that I'll talk about in a little bit are addressing 1 or 2 of these themes. So just a little bit more detail about the 3 themes. As I mentioned, that our first theme is in electrical and optical interconnects. during our spring meeting, we had brought you projects that were using high throughput AI in order to synthesize some new electrical interconnects that are better than copper interconnects that are used in CMOS processes today. And we are also synthesizing them and characterizing them, and you're going to hear from two of our PIs on a project that was eventually funded in Theme 1 on new types of materials for electrical interconnects that would overcome the resistivity scaling challenges of copper interconnects. For our Theme 2, our goal was to develop new fundamental design rules and fabrication pathways that would allow us to integrate different kinds of technologies on CMOS platform. And here we presented projects that were ranging from ferroelectrics to photonics to spintronics. And I'm happy to report that we have, I believe, 2 or 3 projects that are funded in Theme 2 as well. And finally, we have our circuits and architectures theme, where what we're trying to do, as I mentioned earlier, was, well, we have these Themes 1 and 2. Now, how do we put this whole, put everything together, all the raw materials together in order to understand the architectural level benefits of these new devices? And so in that context, we have 2 projects that received good support from our industry members, and we will present them today. Our deliverables obviously vary based on the projects that are being presented, but generally speaking, we will develop these synthesis and fabrication methods. We will be developing simulation tools and cross-layer design solutions, which will be open source. And of course, it's important to consider applications and develop those application-guided benchmarks as well in order to know whether we're able to meet the targets that we have specified for each one of these projects. So some of our technology challenges, we have identified this, and I know that I've presented this earlier as well, but just as a recap, we really have been trying to understand how system-level optimization can enable directed materials and device discovery. So it goes both ways. We're developing new materials and devices, but we're also trying to understand the push and pull between the systems and materials and devices. We are interested in integrating on silicon, and we are interested in translating innovation across digital, analog, and RF platforms. Of course, with all of this comes thermal issues. So one of the things that our center also, we did present I think we presented 2 projects on innovative thermal solutions that were driven by applications and systems. So just a very quick overview of the capabilities and the types of technologies that our center PIs can bring are listed here. We have immense strength in looking at electrical optical interconnects. We'll hear from several PIs today in this space. We have strengths in spintronics, ferroelectrics, van der Waals, layered materials, whether it be for transistor applications or magnetic ferroelectric applications as well, which are memory applications. And then we have new RF devices. We presented several projects on looking at 3, 5, and 3 nitride integration on silicon so that we can get better RF efficiency at high frequency. And again, this brings us back to this challenge of data communication that I was talking about, even at high frequencies. We have projects in heterogeneous integration. And finally, some new circuits and architectures that we have presented include processing using memory, in-memory, and reconfigurable computing. And we will hear from our PI in this as well. So I think this is a slide that I really wanted to kind of address today, the timeliness and relevance of our center. So as I mentioned earlier, if you remember a few slides ago when I was talking about the timeline 2021, so we started working on this idea of energy efficient computing and heterogeneous integration before the CHIPS Act was eventually passed. So our center is actually really timely. So if you look at the model of an IUCRC, this is very similar to a number of the new initiatives that are being launched under the CHIPS Act, where we are an academic institution, but we're working with companies, we're working with foundries, we're working with labs, and we're also catering to creating this next generation workforce so we can establish a pipeline of talent in cross-disciplinary fields. We have a number of hands-on courses that are available at Illinois, both in hardware and software training. We are focusing on chips that allow us to improve the energy efficiency for a powerful information infrastructure. So in many ways, this full stack solution that I was talking about earlier, going all the way from simulation models, material synthesis, metrology circuits, and then driven by applications which are going to create this push and pull kind of a thing, allowing us to innovate across every single element that I've listed over here. Apart from ASAP, our university is actually quite aggressively pursuing a number of the other opportunities in this space. For example, everyone here would be familiar with the DoD Microelectronics Commons Hub. We are participating in 5 proposals. We are co-leading with several of the Midwest schools, as well as in other initiatives as well. We also participated in NSF Future of Semiconductors. Also, this is a non-CHIPS activity. We submitted 7 proposals from Illinois last year, I believe, or maybe earlier this year. Yeah, and I think so far we have received 1 award, and I'm very, very happy to say that our Associate Director of the Center, Professor Ching Zhao, is the lead of the award that was granted to UIUC, and I'm happy to report that I was fortunate enough to be included in that team, along with Professor Swagata Ghosh, who's also a member of the ASAP team. We are also pursuing NIST R&D opportunities, including the ones that I've listed over here, the NSDC, the NAP-MP, Manufacturing USA Institute, and although the metrology R&D, we're not eligible because that's mostly internal to NIST. I'm sure that many of our industry members here will hear from us on some of these initiatives that we are leading or co-leading with others. And then there is also upcoming opportunities with the DOE Microelectronics Science Research Centers. And finally, I'm happy to report that Samsung is actually supporting our semiconductor technology program starting this year. And this is industry funding for developing this educational program. And we have ASAP faculty members who are serving on the advisory committee. So this is a $4 million program specifically targeting the education and workforce development aspects. So I also want to thank Professor Larry Lee, our HMNTL director, for loaning me this particular slide. So quick updates on our April meeting. As I mentioned to you earlier, we held our inaugural spring meeting on our campus, April 20th, 21st, and we had extremely positive and good support that we got from our college and campus level. We had Dr. Melanie Lotz, our Executive Associate Vice Chancellor, our Dean, Associate Dean, Assistant Dean for Research, who all were there in order to give short presentations and introductions to all the wonderful semiconductor-related initiatives that we are pursuing at the university level. At this particular meeting, we also presented talks by ASAP leadership team and NSF. And we had 17 technical presentations from faculty members in our Granger College of Engineering. And these were the projects that our industry members eventually voted on. And we had a great discussion on semiconductor education and workforce development by our department head as well. We had an evening poster and by students, a poster session by students, and a keynote from SRC program manager as well. We recently actually sent out an email with our newsletter since the spring meeting, and the link for that is over here. So if you're interested, you can go to our website and kind of look at this, and I will definitely send these slides to the people that have registered for this webinar. So what else happened at this meeting? Obviously, this meeting was amazing. You can see all the pictures here. We had great representation from our students, very enthusiastically presenting their posters and research, and our industry members showed up and they came to campus and interacted with our students. Out of the 17 projects that we presented to our industry members, they selected top 6 projects to be funded for year 1. And I'll show you which those projects are, and we'll hear from them. We also are thankful to both TSMC and IBM because Carlos is serving as our IAB chairperson, and Oleg, who's here with us, is the vice chair of our IAB. So I'm very thankful to them for helping us, make sure that all the processes, procedures, and everything is working smoothly within the center. In terms of funding for year 1, the total funding for year 1 is $690,000. This does not include any contributions from the university in the form of reduced overhead. So far, I know that many some of the industry members have signed the membership agreement, but we're still waiting on collecting the membership dues. So the funding that we have received so far is 510K. All right, so moving on, what are the 6 projects that our industry members voted on? So they're listed over here. These projects, as you can see, are in different themes. So we have one project from theme 1, which is on topological semi-metals, which we'll hear about today. Project 2 and project 4 and project 5 are addressing theme 2, which is on heterogeneous integration. And then we have 2 projects from theme 3. Today, we're going to present 4 projects to you, the top 4 ones that I've highlighted. And the rest of the 2 projects, projects 5 and 6, as I mentioned to you earlier, we're still waiting on some membership dues. So as soon as that materializes, we will absolutely launch these projects, and you will hear from them during our December fall IAB meeting. If you want to learn more about these projects, the white papers, the slides, everything is uploaded on this particular link over here. I am hopeful that with your membership, we can support more projects, faculty, and students in 2023 and 2024. So what are some of the additional projects that we had presented? So as I said, 17 projects. So you can see the breadth and the depth of the projects that we had presented. We have a lot of projects in computational materials discovery. We have projects, we have additional projects in photonics and integration of 3 nitrides on silicon, high-speed electronics. We also have projects in theme 3, which is on circuits and architectures. So I'm hoping that as our center grows, we will be able to support more PIs and more students in some of the topics that are listed here. However, if you're a new member that wants to join our center and has research needs that you would like us to incorporate into our future white papers, please reach out to us. We will be able to definitely incorporate your feedback as we develop those, the new next year's research needs document. All right, with that, I will yield the floor to our PIs for our first project. So John, you can go ahead.
Wonderful. Thanks, everyone. A pleasure to speak with you today. On the screen, so our project is entitled Topological Semimetals by Superconformal Growth for Seam-Free Trench Fill. And I'll review the science and engineering in a moment. Let me acknowledge in the pictures myself, my collaborator, Greg Girolami. I'm in material science. Greg is in chemistry. On the right is our postdoc, Laurent Souki, and there's going to be a chemistry grad student named in the near future. Very briefly, I've been working in thin film science for over 40 years, the last 20 or 25 in a close collaboration with Greg. Greg is a maker of new precursors for chemical vapor deposition. I work in the kinetics and understanding of the thin film growth and, of course, characterization. So this is the team which in CVD has delivered processes for conformal coating, which in many cases are really competitive with ALD, and then some breakthrough work developing super conformal coating, and that's what we use to get seam-free complete fill of features like trenches and vias. We can go to the next slide. Maybe the other way. There we go. So the statement of the problem is that traditional metal interconnects, when they're scaled down to smaller and smaller dimensions, so thickness and width, have an increase in their resistivity. Of course, the resistance goes up as the cross-section goes down. Here we're saying, in addition, the fundamental resistivity goes up. And that makes the line resistance, and therefore the interconnect delay, really unacceptably long. However, a very scientifically interesting possibility is to work on one or more classes of materials, topological semimetals, which should avoid a resistivity increase at small dimensions, and in certain cases might even have a resistivity decrease. Now, there's a couple classes of these materials, various compounds. You see in the middle, we're listing ones which we think are the best candidates because they're accessible from the point of view of the chemistry and the CVD, and they can be integrated with silicon, and they don't involve bringing highly toxic or unstable substances into the lab. So we have an orientation towards eventual transfer to industry in a practical sense. Next slide, please. So I've mentioned some of these things. Let me come down to the approach, and I want to clarify what superconformal chemical vapor deposition means. If one imagines a deep via or trench with parallel sidewalls, conformal growth can coat these walls. The difficulty is that as the walls, the coating becomes thicker and thicker, the walls grow inwards until finally, inevitably, there's a seam of material in the middle which is not filled. And this is a problem because it's subject to high etch rates during CMP and other steps. So a process like atomic layer deposition is beautiful, we all know, but it's conformal. So it too leaves a seam in the center. The interesting thing about chemical vapor deposition, in addition to having pretty good growth rates, is that you can use unique kinetic features such that the growth is actually faster at the bottom than the top. So as growth proceeds, the bottom, it actually forms a V shape, and with continued growth, the V goes up and out of the feature. I'm demonstrating this with my hands. Sorry, it isn't on the slide. If you're interested in what Greg and I have developed, there on the bottom is a comprehensive review article that lists all kinds of things we've done. By the way, it also includes area selective deposition, enhancement of nucleation for super smoothness, and several theoretical formalisms to predict when you get conformal or superconformal regimes as a function of the precursor kinetics. Next, please. So here's the timeline. I should say we're already working very closely with TSMC, one of the important sponsors here of the ASAP program. And from their perspective, they would like to see more about the superconformal filling on a material which is well known. So introducing a strategically phased approach. So they've suggested we look at titanium nitride, and in fact, there are readily available precursors, no synthesis needed, listed there, which should be really applicable for a low temperature superconformal process. So that's listed as a task we can do from day one, right out of the box. Task two, and here I'll turn it over to my colleague Greg Girolami, is to synthesize new precursors that allow us to do various metal phosphide-based CVD. By the way, none of these will involve bringing traditional phosphine pH3 into the laboratory because we don't want to involve a hazardous gas like that. So Greg, let me turn the floor over to you. Thank you.
Thank you, John. I will be brief. As John mentioned, he has about a 40-year track record of working in the area of thin film growth. We've actually been collaborating for about 25 years. I've been publishing in the chemical vapor deposition field for now more than 35 years. I think, in fact, there's no group at any university that has more experience in CVD than ours does, particularly with regard to transition metal containing phases. We published well over 100 articles on that topic alone. One of the issues with the topological semimetals is that for many of them, there is no current chemical vapor deposition or atomic layer deposition method to deposit them, especially within the thermal budget that you need to pay attention to. So we are synthetic chemists. We have a considerable expertise in the design of CVD precursors and understanding how to do that so that we can meet criteria of stability at room temperature, volatility, as well as the ability to convert under the appropriate conditions to the material of interest. So for these phosphido materials, the niobium, tantalum, and molybdenum phosphides, there is no current technology. That's something that we're going to be looking at in this project. I can give you a little bit of an idea of our approach. It's basically to take a look at the successful technology for depositing nitrides. And since phosphorus is the chemical analog in the same group in the periodic table, we're going to try to use some lessons from the nitride area to try to inform our abilities to our efforts to grow, to design and then grow these films from molecular precursors at relatively low temperatures. Okay. So then, John, I'll turn it back to you for wrap up.
Thank you, Greg. So given new precursors, Greg's group and my group have a protocol for really going through triage, making sure that they have the vapor pressure, check the onset of reactivity. These are done quickly in Greg's lab, and then they come down the street to my lab, where we really evaluate nucleation, growth rate, purity of the phase, crystallinity, and of course, the all-important electrical resistivity. We have Shalu mentioned to this, and I want to underline, just steps away from me is the fantastic Center for Microanalysis of Materials. If you name your favorite nanoscale characterization technique, I can assure you we have it running. There's a staff of 12 professionals over there that maintain all the equipment. It's really one of the jewels here in engineering at Illinois. In addition to what's available in our Micro Nanotechnology Center, for example, especially for resistivity characterization. So we'll go through and put these films through a rapid development cycle, see how far and fast we can get. And the bottom I've listed as task X, which means I'm not making this promise, but clearly on the radar screen, if we get a high-performing molecule for one of these new compounds, we are certainly going to give it a shot and see what we can get in superconformal growth. See if we can even briefly do a proof of concept of what we can do with this. Next slide, please. Okay, that's it for us. Greg, any final comments? Otherwise, I think we're...
No, we're good.
Excellent. Thank you so much. Shalu?
Yeah, thanks, John, and thanks, Greg. All right, with that, I think we will move on to our project 2. So project 2 PIs, please go ahead.
Hi, I'm Linford Goddard, Professor of Electrical and Computer Engineering. I am also the Associate Dean for Diversity, Equity, and Inclusion in the Granger College of Engineering. And I have the great pleasure of being able to introduce our project, which is entitled Photonic Interface for Smart Packaging. It's a collaboration between students in my group and also Kent Choquette, who's in Electrical and Computer Engineering, and Paul Braun, who's in Material Science and Engineering. The two students that are going to be the primary drivers for the project, so Nikita Dugar and also Nisha Kolagatla. Next slide, please. So at a very high level, I'll present the problem statement that we're trying to solve. And it's a problem statement that we've been working on for several years now through various forms of National Science Foundation funding or external funding. It's to be able to route data efficiently in the optical domain, both within a chip and between chips. And the way that we're specifically proposing to do this for the ASAP Center is to combine a method of fabrication called SCRIBE, which stands for Subsurface Controllable Refractive Index via beam exposure, along with vertical cavity surface emitting lasers. The overall goal for what we're trying to do is to be able to make advanced optoelectronic packaging. So we're essentially going to be working on both the glue to hold together the optics and the devices, but also the light source in the vertical cavity surface emitting laser. So shown in the center of the screen is an artistic rendering of our future vision. So this is our long-term 5 to 7 year from now type vision, where we have a series of integrated transmitters on the left-hand side. So we have vertical cavity surface emitting laser arrays that are connected to CMOS transmitter chips. And the areas that we're working on developing, so we're developing higher quality vertical cavity lasers that can be modulated faster and faster. But we're also working on the center sort of artistic rendering part, where we're able to do within the volume of a porous silicon wafer, make micro-optics and waveguiding elements. So we're working really hard on an optoelectronic interposer to be able to connect sources to receivers. The artistic rendering shows diffractive optical elements, coupling lenses, waveguides, and all of this is inside a porous material. And the goal is to be able to do things like wavelength encoding based on having the external diffractive element select the wavelength of the VCSEL, also polarization and spatial mode selection and modulation. Next slide, please. So our approach is to have essentially the combination of two major technologies. The first is to fabricate custom vertical cavity surface emitting laser arrays that have good high-speed bandwidth properties. And then the second is sort of the work that my group and Paul Braun's group really focus on. I should say Kent Choquette's the expert on the VCSELs. So Paul Braun and I are working on the scribe method to be able to fabricate micro-optical elements within the volume of a porous material. So shown on the left, we have a substrate such as silicon, or we can transfer it to other materials. And above it, we have a nanoporous host. So usually this is porous silica. So we create porous silicon, and then we oxidize, or we transfer it, and then we oxidize it. And then we backfill it with photoresist, and we're able to cross-link the photoresist and make essentially polymer-based optics and waveguides. Because it's all inside a nanoporous host, we don't need to print support structures, which in some technologies add additional loss or complication. And we can do very tiny features and do self-alignment as we're writing. So our goal overall is to develop and realize these vertical cavity surface emitting laser interposer chips. And we want to be able to demonstrate the ability to take light from going out of plane from the VCSEL and convert it to in plane in the chip through the use of a vertical bend as shown on the right. So on the right is actually one of the mask layouts of devices that we typically fabricate. We've been fabricating these types of devices for the past maybe 5 years, 4 years, somewhere in that range, which consists of a 15 micron diameter lens, and then there's an adiabatic taper going vertically to convert the mode, and then there's a vertical bend to take the light from vertical orientation to in-plane orientation. So with that background and with that expertise, we want to have two major tasks completed. We want to be able to design and fabricate an array of VCSEL sources that are compatible with the scribe chip that we're going to fabricate that's going to connect the different VCSEL sources and transfer the light from one direction to another. So we're going to use scribe to demonstrate low loss waveguides. And I should say that currently we're able to make devices where we go from fiber onto chip and then back onto fiber with a total insertion loss of 2 dB. It's broadband, so it covers entire wavelength ranges, unlike diffraction gratings, because we're using essentially free space optics to do the coupling. So we want to be able to take these scribe-written photonic interconnects and have them connected to the VCSEL source. So our milestones, the main ones, are to be able to demonstrate the VCSEL array and the chip, which has the scribe-written devices, fully optimize each one individually, and then in the 12th month, combine them and show that we have good functionality. There were a series of tasks that we cut. If companies are interested in the additional work, we were also proposing to look at the modulation characteristics and also look at making novel types of photonic devices that take advantage of our ability to write in 3 dimensions. So I'll pass it to the next speaker.
Thanks, Linford. With that, we will move on to our third project in theme 3. So I know Saugata is here. Saugata, go ahead.
Sure. Thanks, Shalu. Hi, everybody. I'm going to jump one level up the stack here and talk a little bit about what we want to start thinking about from sort of the architecture level on down. We've got a number of students that we've been working on this so far. We are looking potentially to add one more on this, but this is a project that Shalu and I are co-leading as we're trying to look across the stack. Next slide, please. So one of the things that we are, trying to actively target is the idea of the existing design cycle, especially in academia, where we'll work on these new devices, often, sort of in their isolated setting to try to get them perfected and to work as well as we want them to. And then once that's done, we'll transition them up to building the peripheral circuitry and then eventually building the architecture around that. The problem in doing this is that, some of these devices have inherent issues that we want to be able to tackle earlier than, sort of several years down the road when they're quote unquote perfected. Things such as variability during manufacturing, cycle-to-cycle variation, or even how do we organize these into meaningful topologies that we can build architectures and memory arrays out of. And unfortunately, this has sort of been a long-standing disconnect because the architecture community often ends up engaging a little bit later once the device seems like it has a bunch of promise, because we don't want to look at these large-scale devices and large-scale systems without knowing that the device has some good probability of working. And likewise, on the device side, there's a lot of things that you want to work on the device side, so they don't have a good reach into the larger scale architecture community to understand what's going on. And so what we're trying to do is shortcut this so that we can get these devices into a more feasible, scalable form earlier. And in order to do this, we want to be able to enable co-design simultaneously of the devices and the architecture so that we can get a sense early on of what's going on. This essentially requires us to do early stage exploration to understand which devices will succeed. If they're going to succeed, what we want device physicists and material scientists to focus on earlier than later, right? So is it going to be looking at latencies, or is it going to be looking at currents or voltages or reliability and cyclability and things like that? And our hope is that in doing this, by providing tools to start this back and forth earlier, that we're going to allow us to get these things to market sooner, to viability sooner, and to allow us to start thinking earlier about what architectures for devices with new capabilities could look like. But in order to do this, we need to really build out this methodology of simulators that we don't have today. Essentially, we need to make it easy to take these new explorative devices with low effort and plug them into a tool that can allow us to see the potential implications of various architectural decisions that we make well before the devices are fabricated and nanofabbed and tested out. Essentially, we're trying to avoid detailed SPICE simulations at scale, which can take a long time and a lot of effort without yielding lots of results when these devices aren't quite mature enough. Next slide, please. So in order to do this, we're building upon a simulator that we've open sourced over the last couple of years called RacerSim, and we want to develop it into a truly exploratory crossstack tool. RacerSim was our initial effort at trying to take ReRAM device models and integrate some aspects of them into an architectural simulator so that we could do co-design across the device layer, the circuits layer, and the architecture layer. We want to build upon this to essentially make it a tool that can pop in device models that device researchers are building early on, and use that to try a whole bunch of different architectural configurations, a whole bunch of different potential parameters for what these devices could do, and build it out in such a way that we can explore all of this, in simulation well before these devices are found. The goal is to make this work for both conventional memory arrays and for systems that do processing using memory, which will allow us to be at the cutting edge of not only storage, but also logic computation for large data systems. And the goal here is to work with folks in ASAP that are building new devices so that we can incorporate their models, we can look at the impacts of variation and architectures on them, and we can help make the devices coming out of ASAP more robust, because we'll be able to give them quick feedback on the types of things we want to change. I've got a bunch of milestones over here. The long and short of it is that, we hope by the end of the year to be able to have an extended simulator that can support plugging in these device and circuit models and actually giving us some early exploration results. And we hope to work with the ASAP device designers to get some report back to you guys on some of the viability and wish lists for each of these devices and what we'd like to do. So with that, hopefully that gives you a little bit of an overview of what we're looking at, and looking forward to your questions during the Q&A.
Thanks, Sakara. All right, so we're ready to move on to the last project presentation for today. So Professor Arend van der Zande is not going to be able to join us because he was called in for jury duty. And I've been told that he could not get out of it. So I'm going to cover for him. So our fourth project is also in our second theme of heterogeneous integration. It is entitled Strain-Induced Mobility Enhancement in 2D Materials Transistors. Arend is a professor in mechanical science and engineering, and his graduate student, Kevin Zhao, I hope is here to take questions related to the project. So for 2D materials, these are naturally atomically thin, and therefore they are a prime candidate for replacing silicon and CMOS technologies. And they also have some excellent properties, electronic, mechanical, as well as optical properties. But there is still a very big gap as to how the CMOS processes, such as the deposition of thin films, would affect the strain, doping, as well as the defect profiles in these 2D materials. And because of that disconnect, what ends up happening is that there's a huge amount of variance that is reported in the literature for the performance of these devices. So really the goal of this project is to develop new approaches to rationally design these 2D materials by gaining control over some of the effects that I have mentioned. There's also a huge opportunity because for a number of decades now, electronics has really profited from strain that is induced by the deposition of high stress materials on top of transistors, which helps them improve the electron mobility. So really, if we can gain control and understanding of how to induce strain in these 2D materials, we can potentially develop transistor structures that have superior performance. So Professor van der Zande's group has actually developed methods. They also have a lot of knowledge in this field of thin film deposition and really just controlling the strain and doping in these 2D materials. So in terms of the approach, the figure at the bottom shows what they're going to be able to do. They are going to sequentially deposit these thin film dielectrics, which can induce tensile or compressive stress onto these field effect transistors. And they are going to target molybdenum sulfide and tungsten selenide to begin with in this particular year. They actually have developed a method for extracting local strain and doping using Raman. And they also have models that can explain how strain is transferred into the 2D material. So they are very uniquely positioned to carry out the work that is described over here. I'm not going to go into the milestones in very much detail, but I hope that if you have any questions related to these milestones, please reach out to Arend, and I'm sure that he can respond to that. But really, the impact here is huge because they can really define new strategies to understand and design the relationship between processing, structure, electronic properties that allow us to integrate these materials within a CMOS platform in a heterogeneous manner. And they can also use the existing CMOS techniques in order to enhance transport across a wide range of these 2D materials. So with that, we are done with our project presentation. But I will remind everyone that there are 2 additional projects that we're hoping to fund, and the PIs of the projects are here. Our first project that we intend to fund will be on junctionless back-end of line transistors, which Professor Jing Zhao has proposed. And then there is a second project that Professor Wenjuan Xu has proposed on ferroelectric reconfigurable computing. So we are hoping to fund those projects later in the year. Now, one of our very unique capabilities as a center is that we're able to access all of the materials, our research lab capabilities, our device fabrication capabilities that are housed at our micro and nanotechnology lab, as well as our coordinated science lab. The first picture over here, which is for MRL, we really have great capabilities in synthesizing novel materials and excellent materials characterization techniques as well. Our HMNTL lab, which is in the middle, that actually is an 8,000 square feet of clean room for nanofabrication of electronic and photonic devices. We also, I believe, have 2,000 square feet of teaching clean room here, and there's a 3,000 square feet of a bio-nanotechnology lab for making biosensors and conducting research in biophotonics. And finally, our coordinated science lab is where we have a lot of work that is happening at the intersection of circuits, computing, control, and communication. I also want to emphasize that CSL is actually the home of multiple faculty members that are involved in Jump 2 centers. And I know that Professor Naresh Anbag was here. He's also a co-PI of our center, and he's also involved in multiple Jump 2.0 efforts. We do have state-of-the-art equipment. We have best in the world metrology. We're also trying to add capability in the growth of new ultra-wide bandgap materials. Hopefully in the 2023, maybe 2024 timeframe. The goal here is that this MBE would allow us to do regrown contacts and very high aluminum content, algan, scandium-based alloys as well. Our E-beam patterning is also, I would claim, is best in the world. And for materials and device metrology, I think we're constantly upgrading our equipment. We were recently approved for plasma enhanced ALT, and so hopefully this can allow us to handle air sensitive materials. And this capability is also expected to be housed maybe later this year or early 2024, and all of this will be available to our ASAP faculty members to conduct their research. That brings me to the last portion of this webinar today, which is on education and workforce development efforts. We are very, very strongly supportive of all of the CHIPS Plus Science Act initiatives that are coming out, and within that is this great need for developing curricula and developing methods where we can train these students in cross-disciplinary fields and make them ready in order to tackle these jobs that would be coming up in the semiconductor fabrication, manufacturing, as well as computing domains. Illinois actually offers more than 75 courses in hands-on training in IC fabrication, processing, device physics, going all the way up to quantum information and communication. I'm also very excited to report that we are actually going to be launching a college-wide undergraduate minor that is transcriptable for our undergraduate students starting in fall 2024. The goal of this minor is that this would encourage students from diverse disciplines within the college, such as physics and industrial engineering and nuclear and plasma and materials mechanical, to pursue these courses and develop that hands-on training that they need in order to succeed in these careers. Our team, basically our ASAP faculty members, many of us are actually serving on the committee that is developing this, or at least pushing for this undergraduate minor. So we're happy to kind of take the feedback from our industry members to really shape the minor program and even ask for your help to fund curriculum development in order to meet your emerging needs. Our center will also apply for a number of NSF funding opportunities that are available to us. So for example, we hope to apply for the intern NSF funding, which would allow our students to actually pursue internships for up to 9 months in our member companies, as well as bring in undergraduates to support the industry recruitment efforts. And we are working on this, and fall 2023 is going to be our time when we will be putting in all of these additional applications. We will be submitting these applications to NSF. All right. With that, I want to actually tell you a little bit about the very first thing that we did as part of developing this undergraduate minor. We have recently, this semester, launched a new course called ECE 298, and it is the title is pretty cool. It's called the Semiconductor Chips Revolution. I'm one of the co-instructors of this course, and this course is a seminar course, and we're bringing in industry members, national lab, DoD members in order to talk to our students and present different aspects of the sort of career opportunities that might be available and how semiconductors are useful within their organization and so on. We want to encourage students to develop this interaction between experts from academia and industry through these guest lectures. We want to motivate them to pursue semiconductor-related courses. So this is a 1 credit hour seminar course, and I'm very happy to announce that we will have companies that I've listed here that have already committed to a time to coming to campus. We have TSMC, Intel, Micron, Tesla, Samsung, Marvell, Synopsys, ST Microelectronics, Santia, and Fermi Lab. The highlighted companies are the ones that are that were present, that have been supportive of ASAP from the very beginning, and I'm looking forward to additional engagement with the companies that are going to come here. Current enrollment actually, as of today, is 75 students. We have students from EC, materials, physics, and we also have students from philosophy, which is quite interesting. So this is very exciting, and I am very thankful to everyone who's coming to present. If you would like to come to our campus to present a seminar for future or you have some recommendations for how the ASAP related projects can be included in our curricula, please do email us and let us know. We will be able to work on some of those things. So with that, I'll just tell you our membership model. We have a full membership available for 60K. And obviously you can get more votes on our advisory board for up to 120K. So you can get 2 votes on that. We do have members in our center that are actually giving us 120K for 2 votes on the board. Then we have associate level membership, which is basically reserved for small companies, startups, and so on. And we have affiliate memberships. And there are differences in how these members can interact and engage with ASAP. So if you're interested, I can let you know a little bit about that later on. And finally, if you are interested in supporting us, I highly encourage you to please email us. One of the benefits is you're able to shape all of our, or help us figure out how to support the education and workforce development needs of our students better, but also really shape the roadmap in the space of heterogeneous integration and advanced computing. That would be excellent. We are going to be able to draft research needs document based on your feedback. So your feedback to us is really critical in developing good projects for later on. So again, reach out to us and we'll be happy to give you additional information. So with that, I think I am really happy I'm on time. This is 2:59 p.m. Super amazing. So with that, I will summarize. Our center has 3 themes. We are an IUCRC. We are going to develop projects that address themes, all these themes, in order to realize our vision of creating or of reducing the data communication challenges for different sectors of the semiconductor industry. We don't want to just develop devices for the sake of developing devices. We also are going to be guided by application and systems. We are bringing you diverse expertise from PIs and students, and we will sustain our workforce development activities to meet those national needs. With that, I will open the floor to any Q&A from the audience. Thank you so much for being here.
So Shalu and all the presenters today, thank you very much for the project introductions. And it's going to be an exciting year coming up, right? So yes. Just wish the best. And I don't have any particular questions. Just one that came to mind during the presentation of the optical waveguide when you